This week, we're going to look at some consequences of the chain rule. Now, three things we're going to do first are the derivative of an inverse function, something called implicit differentiation, and something called logarithmic differentiation. Now, we'll start with the derivative of an inverse function. But before getting into that, let's just remember what the chain rule says. The chain rule, remember, tells us how to take the derivative of a composition of functions. And it says, so we'll recall, the chain rule says the derivative with respect to x of a composition, so we'll call that f of g of x, equals the derivative of f, leaving the inside alone, and then times the derivative of g, derivative of that inside function. Now, we're going to use this to find the derivative of an inverse function. And we're going to remember one of the one of the parts of the definition of an inverse function. So remember, the inverse function was defined so that f composed with f inverse equals x, and f inverse composed with f equals x for all x in its domain. And we're going to remember that and apply the chain rule on one of those compositions. So first, derivative of f inverse of x. And we're going to get a formula for this. So we'll recall the definition of the inverse function. And I'm going to write it backwards. I'm going to write it with x on the left side so that the rest of the equations, it's a better organization to write it on this side. So remember, the inverse function, one of the identities it satisfies is that f composed with f inverse equals x. F composed with f inverse results in x. And now what we're going to do is differentiate both sides. So differentiate both sides with respect to x. On the left side we get 1. The derivative of x with respect to x is 1. On the right side, what do we get? Well, we have a composition of functions on the right side. So the derivative of a composition is given by the derivative of the outside function, leaving the inside alone, but then times the derivative of the inside. And I'm going to write that, I'm going to use a bracket here so it stands out more. The derivative of the inside. So right here on the left side, derivative of x is 1. Derivative of the right side is the derivative of the outside function, which we have here, then times the derivative of the inside. Notice the derivative of the inside is the derivative of f inverse. So right here, I'll just put an arrow and say this is the derivative of f inverse. F inverse prime. And our goal here was to find the derivative of f inverse. Well, right here, there's the derivative of f inverse. But we haven't solved for that, so let's solve for that by dividing both sides by this thing in front of it. So divide both sides by f prime of f inverse. So solving for f inverse, so to say, so we get the derivative of the inverse. There is a bit of notation here. Derivative of f inverse, divide both sides by this, so you get equals 1 over f prime of f inverse. So right here, all we did was divide by this piece. And we have a formula for the derivative of any inverse function. So if we want the derivative of an inverse, all we have to do is follow that formula. So let's do one example of this. Let's prove, so up to this point we have the derivative of the inverse sine function is what? 1 over root 1 minus x squared. But now we're going to prove, using this formula, prove the derivative of the inverse sine of x is 1 over root 1 minus x squared. And we're going to use this formula to do that. So how do I want to write this? Well, we have f in our formula, so let's let f of x equal sine of x. Well, if we let f of x equal sine of x, then this formula up here will give us the derivative of sine inverse. To substitute into this formula, we're going to need f prime. So f prime, well, the derivative of sine is cosine. So f prime is cosine of x. So I'm going to go over to this board. Am I? Yeah, I guess I will. Then, the derivative of the inverse sine, so sine inverse derivative of x, using that notation, equals 1 over f prime of f inverse. So cosine of sine inverse of x, just using this formula with f of x equal to sine of x. Now, that denominator simplifies a little, and remember the trig functions operate on angles and give out numbers. The inverse trig functions operate on numbers and give out angles. So right here, the inverse sine of x is actually an angle in a triangle. That's going to simplify. Which triangle is it? Well, let's draw the triangle that has inverse sine of x in it. So how do I want to draw it so it looks nice? It's theta down here. If that is theta, and that is x, and that is 1, then sine of theta is x. Remember, the inverse sine of x is the angle whose sine is x. So right here, this angle's sine is x. So notice, let's notice a little lower since I want to label that other side. Notice theta equals the inverse sine of x, because sine of theta is x. This is a right angle. Now we have two of the sides on this. We want cosine of theta. Well, cosine of theta is this side over, in this case, 1. This side is what? Given by Pythagorean theorem. This side is root 1 minus x squared, because what? This squared plus this squared equals 1 squared. So this side is the square root of 1 squared minus x squared. Well, now cosine of theta is what? Well, let's just write it here. And cosine of theta is root, let's write it correctly, is root 1 minus x squared over 1, and I'm not going to write the over 1. So this simplifies to 1 over root 1 minus x squared. So we had the derivative of inverse trig functions. I gave them to you a couple weeks ago. But right here, we could actually use the derivative of an inverse trig function, or the derivative of an inverse function, to derive a formula for the derivative of an inverse trig function. And the other 6 trig functions follow similarly. It might be worth trying one of the other ones. Maybe try tangent. The derivative of inverse tangent is 1 over x squared plus 1. So try that one. But next, we will do something called implicit differentiation. Now, all of the things we've been taking derivatives of so so far have been functions. But what if we wanted to find, what if we had this graph? That's a terrible circle. So let's observe a circle is not a function, because a circle does not satisfy what? The vertical line test. A circle is not a function. But what if we want to find tangent lines on this circle? What if we wanted to do our applications in Chapter 4 using this circle? Well, we don't know how to do that. But what we can do is consider an equation for the graph of this circle. Let's take it to be radius 5. So let's just say this is the circle of radius 5. I'll write it over here. X squared plus y squared equals 5 squared. So let's call this the circle of radius 5, centered at the origin. That's not a negative. That was supposed to be an extension of here. I'll just get rid of that. X squared plus y squared equals 25. Right here, the graph defined by this equation is not a function. But it does still define a graph. And what if we want to find tangent lines? Well, what we can do, using this equation, y is not a function of x. X is also not a function of y. But this equation defines y in terms of x. It doesn't define y explicitly in terms of x. And if you tried to solve this for y, you'd have to make a choice. But it does define y implicitly in terms of x. So this equation defines y implicitly. Implicitly in terms of x. Meaning we can't solve it for y without having to make a choice. In this case, our choice would be a positive or a negative square root. When we have an equation where y is defined implicitly in terms of x, we can find the derivative of y with respect to x using the chain rule and this method called implicit differentiation. So let's write an example. And it'll be the same curve. Example. Find dy dx for this equation relating x and y. Let's find dy dx. Well, what we can do, we'll think of y as being kind of a function of x. Not a perfect function of x, but kind of a function of x. And we'll take that into account when we differentiate both sides with respect to x. So first step, differentiate with respect to x. Respect has a c. And what that means is our variable that we're taking the derivative on is x. And that's what we have been doing. Well, if we differentiate with respect to x, on this side, well, x squared, we get 2x. Now, y is not a function of x. But what we can do is think of this y as having a bunch of x's. So let's say a bunch of x's. Not x's. That's not going to say. A bunch of x's. Y is kind of a function of x. Well, we know how to take the derivative of something which has a bunch of x's and is squared. If we needed to take the derivative of sine of x squared, well, we could do that using the power rule and the chain rule. The derivative of sine x squared is 2 sine x to the first times the derivative of the inside. That's what we will do here. The derivative of this bunch of x's squared is going to be given using the power rule. So we have something squared. The derivative is 2 of those things to the first power but then times the derivative of the inside. The derivative of the inside is y, and we're taking derivative with respect to x, so the derivative of y with respect to x is dy dx. So here, taking derivative with respect to x, x squared turns into 2x, y squared turns into 2y dy dx from the power rule, giving us 2y to the first, then multiply by the derivative of the inside. Equals on the right side, derivative of 25 with respect to x is 0. As x is changing, 25 does not change. 25 remains 25. Well, that's great. Our goal was to find dy dx. Well, there it is. But we don't want it like that. We want it solved for dy dx. So let's solve this for dy dx. So next step, solve for dy dx. Solve for dy dx. Well, solve this for dy dx, we would what? Subtract 2x from both sides, and then divide by 2y. Divide both sides by 2y. The 2's go away. And we've solved for dy dx. Negative x over y. Notice there are x's and y's in our answer. When we do this implicit differentiation, well, maybe I should say, when y is not explicitly solved in terms of x, we will have y's in our answer. Now, let's make one observation about this equation, 2x plus 2y dy dx. Let's make one observation. This dy dx shows up from the chain rule. The chain rule says the derivative of something squared is 2 of those things to the first times those things' derivative, times squiggly line prime. Whenever we take the derivative of a y variable with respect to x, we're going to have to apply chain rule. So one thing you can think when you're doing these implicit differentiation type questions is when you take the derivative of a y piece with respect to x, you always throw a dy dx on it. And that's because of chain rule. It's very useful to keep in the back of your mind that that shows up because of chain rule. The next thing we do this week, the lecture video 8.2. This is week 8, right? Yeah, last week was 7. Lecture video 8.2 is going to be on related rates, which I think is quite complicated. And the most complicated part about related rates is actually about the same as that. So keep in mind, dy dx shows up from the chain rule. Whenever you take the derivative of a y here with respect to x, a dy dx is going to appear. And then you have to solve for dy dx. Now, I like the dy dx notation for this because when you come up with that equation, 2x plus 2y dy dx equals 0, when you differentiate with respect to x, the dy dx's are, I mean, they really pop out in my mind. But there is an alternative notation using the other derivative notation. I find that most Calc 1 students tend to prefer the alternative notation. I assume because it's less writing. When I took AP Calc and we did this, I also did the alternative notation. Because it was less writing. But now that I teach it, I like the more writing method more. When I was taught it, I was taught with the more writing method. Instead of writing all dy dx, you could just write a y prime every time you take the derivative of a y piece with respect to x. You could just write a y prime. I don't like that as much. Yeah, I don't like it as much. I mean, I think this equation is a little more confusing, or maybe a little easier to make an error on. But you are allowed to do that, of course. Solve for y prime afterwards. Example. So that equation was a circle. Well, let's write the example first. Find equations for all lines tangent to x squared plus y squared equals 25 when x equals 3. So find equations for all lines tangent. This is a circle. Looks like this. When x equals 3, let's say it's there. This is a circle of radius 5, so this is 5, so 3 is somewhere in there. When x equals 3, there are going to be 2 corresponding y values. And because of that, we're going to get 2 tangent lines. So up until this point, we haven't had that situation because all we've been dealing with have been functions. But now this curve is not a function, so we're going to have multiple tangent lines. But find equations for all lines tangent, we still want equations of tangent lines. When you need an equation for a tangent line, you need a point and a slope. So let's find the point first. In this case, there will be multiple points. To find the points, we need, well, we have the x values, so we need the y values. X equals 3, so we get 9 plus y squared equals 25. Subtract 9. Y squared equals 16. And here we want all y values. So we have y equals positive 4 or y equals negative 4. And that is consistent with that drawing I erased. You got one that went in the positive y direction and one that went in the negative y direction. So let's see, we're going to have 2 points. Let's do it like this. So there's 1 point, and we're going to want the slope, and then we want the other point, 3, negative 4, and we're going to want the slope there as well. So we found our point, well, we found our points. Now we need to find the slope. How do we find the slope? Well, we found dy dx. So dy dx, we found it in the previous example. Dy dx was negative x over y. So negative x over y here is just negative 3/4. And similarly, for this other point, dy dx also equals negative x over y. Negative x over y in this case is negative 3 over negative 4. And negative 3 over negative 4 is just 3/4. So this one we have a point and a slope, so y minus 4 equals negative 3/4, x minus 3. And this one down here we have another point and a slope, y minus negative 4 equals what? 3/4 times x minus 3. So here, find equations for all lines tangent to this curve when x equals 3. We needed to first find the point or points. In this case, there were 2 points. And once we found the 2 points, we found the 2 slopes, and then we found 2 equations. Let's do another example. Example. Find dy dx for this equation. 4x to the 5th plus tangent y equals, what does it equal? Y squared plus 3. So first, you could try to solve this for y. It won't work. But next, we have an equation relating x and y. So what we can do is differentiate it implicitly. So differentiate with respect to x. And every time you take the derivative of y, you're going to apply the chain rule. Derivative here, the derivative of x to the fifth is 5x to the fourth. 5 times 4 is 20, so we get 20x to the fourth. Derivative of tangent of y. Well, derivative of tangent y with respect to x, we take the derivative of tangent normally. Derivative of tangent is secant squared of y. I'm going to write a little smaller so that fits on the one side of this board. Derivative of 4x to the fifth, this is 20x to the fourth, plus secant squared of y. But then y contains lots of x's. So we need to multiply by the derivative of this inside function. The inside function is y. What is inside tangent is y. So we need to multiply by the derivative of that y, which is dy dx. And then on the other side, derivative of y squared with respect to y. Let's make it a little more interesting. We did a y squared in the previous examples. Let's make this y to the 23rd. I think a bug just landed on me. Yeah, there's a moth in here. That's great. That's going to distract me the entire time. So where was I? Y to the 23rd. So I changed that to 23 because we had a y squared in the previous example and I didn't want to have to erase something, so I just threw a 3 on it. But the derivative of y to the 23rd, it is a function to the 23rd. So its derivative is 23 of them to the 22nd. And then you multiply by the derivative of the inside. The derivative of the inside is y, so the derivative of the inside is dy dx. And then plus the derivative of 3, which is 0. Now, right here, there's a moth somewhere behind me. I don't know where it is. I don't like when I don't know what's going on behind me. So now, our goal, remember, was to find dy dx. Well, notice here we have, there's a dy dx. There's a dy dx. That was a good stroke of luck. That dangerous moth just went out the door, so I was able to close the door on that moth, preserving my sanity for the rest of this video. So we have 2 dy dx's. We still want to solve for dy dx. What if we had this equation? What if it just 5 equals, well, no, not equals. 5 plus 4x equals 3x. What if I said solve this for x? What would you do? Well, you would say, here's an x, here's an x. Put them together, and then divide. Put them together, you get 5 equals negative x, divide by negative 1, multiply by negative 1. And you get negative 5 equals x. We're going to do the same thing here. We need dy dx, so we're going to combine those terms. So let's do that. I'm going to put this on the right side. So I'm going to put everything with a dy dx on the right side, everything without a dy dx on the left side. So 20x to the fourth is on the left, let's leave it there, equals 23y to the 22nd dy dx minus secant squared of y dy dx. So all we're doing is moving things with dy dx to the right side and moving things without dy dx to the left side. Well, now, both of these terms have a dy dx. So we can factor that out. So on the left side, or on the right side, we can factor out a dy dx. Factor out a dy dx here, you're left with 23y to the 22nd. Factor out a dy dx here, you're left with a negative secant squared of y. Well, what if you had this 5 equals 7x, and I said, solve this for x? Well, what you would do is get rid of the 7 using division. And that's all we're going to do here. I'm going to write my conclusion since I don't want to write on the wall. So I'll say, so dy dx, divide both sides by that, equals 20x to the 4 over 23y to the 22 minus secant squared of y. So all we did here was take the derivative with respect to x. In doing so, all these dy dx's showed up, and then we combined the things with dy dx, combined the things without dy dx, factored out a dy dx, and then divided. And we have this. Let's do another example. Let's do another example. Do I have another example? I do somewhere. Let's do this example. Find dy dx. I'll still write on this side. Y cubed cosine x equals e to the y plus sine of x. Y cubed cosine x is e to the y plus sine of x. Well, we're again going to differentiate implicitly. Differentiate with respect to x. Differentiate with respect to x. What do we have on the left side? We have a y cubed, and then we have a cosine x, and they're multiplied. They're multiplied. So we're going to have to use a product rule. We have two things multiplied. To find their derivative, you have to use the product rule. You can't just say 3y squared dy dx times negative sine x. You have to use the product rule. This is a product. So what do we get? Well, the derivative of y cubed is 3y squared, and then apply chain rule. We're differentiating with respect to x. Apply chain rule. The derivative of the inside is dy dx. So this is derivative of the first, leave the second alone, plus the first times the derivative of the second. The derivative of the second is negative sine of x. And notice, we're taking the derivative of cosine of x. That doesn't have any y's, so we can take that derivative normally. And notice also, I changed that plus to a negative because the derivative of cosine is negative sine. Well, that's great. What do we get on the right side? On the right side, we have e to the y. Well, e to the y's derivative is itself. But that's a y, so we have to use the chain rule. So e to the y times the derivative of the exponent, which is dy dx. And then plus the derivative of sine. Derivative of sine is cosine. Okay? Our goal, remember, was to find dy dx. Well, there's a dy dx. There's a dy dx. So let's put everything with dy dx on one side and everything without dy dx on the other side. So I'm going to move this e to the y thing to the left side, and I'm going to move this negative y cubed sine x to the right side. So I'm going to put everything with dy dx on the left, everything without dy dx on the right. And I'm also going to factor out a dy dx in this same step. Because I know I'm putting everything with dy dx on the left side, so I know everything's going to have a dy dx. So let's just factor out a dy dx. Take a dy dx out of here. You have a 3y squared cosine x. We're moving this to the other side, so we're subtracting that. Take a dy dx off of it. Negative e to the y. And then on the right side, cosine x is already here. And then we're bringing this term to the other side, so that's a positive y cubed sine of x. Well, now all we have to do is divide by the coefficient on dy dx. And so I'll write that over here again. So dy dx equals what? We're dividing this side by that quantity. So cosine of x plus y cubed sine of x all over 3y squared cosine of x minus e to the y. I'm going to put that in a box so there's separation from the rest of the equation. So again, all we did was take the derivative with respect to x and apply the chain rule. And because of the chain rule, all of these dy dx's appear. And then you just have to solve for dy dx. The next consequence of chain rule we're going to look at is, we're going to use the chain rule to take more derivatives. And here, we're going to use logarithms to help us take some derivatives. So let's what do I want to observe first? Do I want to consider that, or do I want to observe this first? Let's recall. We can use logarithms to take a function like this So let's take this function, that's a square root. So we have x squared minus 7x to the fifth, root 4x plus 7 over x times 5 minus 3x to the fifth, all to the 7th. So recall that this function can be broken into a sum using a logarithm. This was the last question, well, with different numbers. This was the last question on exam 1. And what do we mean by this can be broken into a sum? Well, log of, let's see, how much room am I going to need? Let's start here. That is log of x squared minus 7x to the fifth, 4x plus 7 to the half, x times 5 minus 3x to the fifth, all to the 7th. The log, we're going to use a natural logarithm, and we'll see why in a moment. You could use any other base if you want. We're going to use a natural logarithm base. We can split this using the logarithm rules into 5 log of x squared minus 7x plus a half. Remember, the exponents go out in front. Plus a half log of 4x plus 7 minus, remember, in the logarithm of a quotient, the things on top get a positive sign, the things on the bottom get a negative sign. So minus log x minus 7 log of 5 minus 3x to the fifth. So what we did was take this large fraction and we threw a logarithm on it, and putting that logarithm on it turned it into this sum. So that's observation number 1. A logarithm can break apart the fraction like this. The next thing we're going to recall is that we can take the derivative of a logarithm function. But it also has a convenient form. Am I going to want to erase that? Yeah, I guess I will erase this. I'm going to wind up rewriting it in a moment, but I don't believe I have the board space to avoid that. Maybe I do. Doesn't matter. I erased it. This is a ladybug up here. Next thing we'll recall. we can take the derivative of a logarithm. And it has a convenient formula. The derivative of log of something with x's in it, the derivative with respect to x, is 1 over that thing. But then, using the chain rule, you need to multiply by the derivative of that thing. And we'll call that square prime. Maybe I'll put a 5th line on this so they all have 5 lines. So the derivative of a natural logarithm can be written like that, but notice you can just write that as one fraction. As thing prime over thing. So there is our second observation. And we're going to combine those two observations to take the derivative of that first function. So let's do that. Let's see, how much space am I going to need? Okay. A good deal. So, example. Find dy dx for this function. Y equals what we had before. X squared minus 7x to the 5th root 4x plus 7 all over x times 5 minus 3x to the 5 all to the 7. Find dy dx is. Now, you could just use the quotient rule. We could do this using the quotient rule. We're going to use a logarithm, however. And what we're going to do is take a logarithm on both sides and then differentiate implicitly. So first, take a log of both sides. So take, maybe I'll spell take right the third time. On the third take. Take log of both sides. And what do we get? Well, on the left, we get log of y. On the right, remember, the logarithm causes this to split apart. That's a 7, not a 5. So remember, the logarithm will cause that fraction to split apart. And now we have an equation relating x and y implicitly. So next we're going to take derivatives, differentiate with respect to x. Let's just say that is an abbreviation, differentiate with respect to x. And what do we get? Well, here remember, y is implicitly a function of x. So we get 1 over y times the derivative of the inside, which is dy dx. So on the left side, we have 1 over y, dy dx. On the right side, all we have are functions, are logarithms with only x's. We don't have any implicit differentiation on the right side. We take the derivatives normally, remembering that the derivative of log of something is something prime over something from the chain rule. This should say derivative of log of something. And we're going to do that with all 4 of these pieces on the right side. The 5 stays there. Now 5 times 3 is not 35. 5 times 3 is 15. So what do we have here on the right side? Well, the derivative of 5 log of that, the 5 you carry through, Derivative of log of something is 1 over the inside times the derivative of the inside. Derivative of x squared minus 7x is 2x minus 7, and the 5 carries through. Here we have a half. Derivative of the inside is 4. The inside is 4x plus 7, so we have 4 over 4x plus 7 times a half. Here we just have an x on the inside, so the derivative there is 1 over x. There's a negative sign, that carries through. And here we have a negative 7, so the negative and the 7 carry through, times 1 over the inside, there's 1 over the inside, times derivative of the inside, negative 15x to the 4. Well, that's great. What did this question actually ask us to do? This question said find dy dx. We did all that work, and we did not find dy dx. We found 1 over y, dy dx. So how do we find dy dx? How would you solve for x, for half x equals 5? Well, you'd get rid of the half by multiplying by 2. So we're going to do the same thing here. We're going to get rid of this 1 over y by multiplying everything by y. So I'll say solve for dy dx. Solve for dy dx. Dy dx equals, what does it equal? Well, it equals y I'm going to do a board trick here. So y, and then times all of this. And notice I'm leaving a gap. Gee, why could I be leaving that gap? I don't know. Let's see. I'm going to distribute that 5 through, I guess. 10x minus... Okay, 5 times 7 is 35. I guess that showed up somewhere in this. 10x minus 35 all over x squared minus 7x. The 4 and the 2 reduced to a 2. I should not have finished that. Minus 1 over x. Negative 7 times negative 15, 105. So plus... Negative 7 times negative 15 is 105, because it's what, 35 plus 70? So plus 105, x to the 4, all over 5 minus 3x to the 5th. So we wanted to find dy dx. Well, here's dy dx. But when you can get rid of y's, you should get rid of y's. So we would get rid of that y. Well, y just equals this up here. So let's replace this y with that original function. X squared minus 7x to the 5th root 4 plus 7x. I can't even write it. 4x plus 7 all over x times 5 minus 3x to the 5th all to the 7th. You don't have to distribute that through. So what we did here, we used logarithms to our advantage. We used the logarithm to crush that function up, and then we did the derivative of logarithms. But then we had to solve for dy dx. dy dx, multiply everything by y, equals y, which is all of this, times all of that with some simplification. Now, this is one way we can use a logarithm to take a derivative. If you want, you can use the quotient rule, take the derivative there, and check that it equals this thing we got in the last step. You might need to simplify, well, you might need to simplify both of them to see that they're the same. Don't ask me to do that, because I'm not going to do that. They are the same. But if you want to practice your derivative taking with the quotient rule, feel free. Well, the last thing we're going to do here is another form of logarithmic differentiation. So we're going to recall the derivative of x to the n with respect to x is nx to the n minus 1. That's the power rule. We're also going to recall n is a number up there, any number. We're also going to recall b here is any positive number. Derivative of b to the x with respect to x. We can find that. B to the x log b. Well, that first one has x's in the base. It's a power function. This next one has x's in the exponent. That's an exponential function. But what if we had x's in the base and the exponent? What does that equal? Well, for the next few minutes, it will equal a bunch of question marks. 3 question marks to be exact. That first question mark is a pretty nice question mark. I'm actually very happy with that question mark. That might be one of the best question marks I've ever drawn. Fortunately, I have my phone here, and I can use that to take a picture of that fantastic question mark. There, I'll take 3 in case they're unclear. That's a really nice question mark. And the dot isn't perfectly placed underneath it, but the rest of it, that's a really nice question mark. We want to take the derivative of x to the x. How are we going to do that? Well, this is under the topic of logarithmic differentiation. So what we're going to do, another way of phrasing those 3 question marks, those 2 shoddy question marks, and then that 1 really nice question mark, is find dy dx for this function, y equals x to the x. If we do that, then we will find the derivative of x to the x. Well, all we're going to do is introduce a law. I hope that question mark showed up as nicely on camera as it did right in front of me. What we're going to do here is introduce a natural logarithm. And what does the natural logarithm do for us here? Well, let's say take log on both sides. Ranting about a fantastic question mark, then I draw a 3-dotted colon. What happens if we take the natural log on both sides? Well, the left side we get log y. What do we get on the right side? We get log of x to the x. So we have log y equals log of x to the x. How does that simplify x to the x? Well, we can use our exponent rules. If we use our exponent rules, that right side simplifies to x log x, which is a product. And we know how to take the derivative of a product. So now, let's take the derivative. So differentiate with respect to x. Well, on the right side, on the left side, we're still going to get 1 over y dy dx. Derivative of log y, 1 over y times the derivative of y times dy dx. On the right side, what do we get? Well, the right side we have just x's. We do have a product, however, so we need to use the product rule. So we get what? 1 times log x. The derivative of x is 1. So 1 times log x plus x times the derivative of log x. So we get 1 times log x plus x times 1 over x. Well, we want to find dy dx. There's dy dx. Dy dx has this 1 over y in the way. This 1 over y is preventing this equation from being solved for dy dx. So all we'll do is multiply by y. So we get y times 1 times log x, that's just log x, x times 1 over x is just 1. So that simplifies a little. A nice simplification. So you should do nice simplifications. But right here, remember, we have y already solved in terms of x, so we should get rid of that y. Just replace y with x to the x. So dy dx here. Introduce a logarithm. Introducing a logarithm turns that right side into a product. Then take the derivative using implicit differentiation. You get 1 over y dy dx. Use the product rule. Solve for dy dx, which we have here. And replace y with x to the x. Replace y with x to the x because that's what y is. And let's do one more example. Say we have more than just x to the x. Let's say we have cosine x to the x squared. So let's say find dy dx for this function. Y equals cosine of x to the x squared. So let's change that from being just x to the x. Let's make it cosine x to the x squared. Well, we're going to follow the same procedure. We're going to throw a logarithm on both sides. So on the left side, we have log y. On the right side, we're going to use our logarithm rule. The right side, we have log of cosine x to the x squared, so that x squared comes out as as multiplication. We get x squared log of cosine x. And then we're just going to take the derivative on both sides with respect to x. So again, using chain rule, we get 1 over y dy dx. On the right, we have a little bit more annoying of a derivative to compute than before, but it's still a derivative from 2 weeks, or from last week with chain rule. We have two things multiplied. So again, we'll use a product rule. Derivative of x squared is 2x. So we have 2x, leave the other one alone, plus x squared times derivative of log of cosine x. Well, what's the derivative of log of cosine x? Well, the derivative of log of anything is 1 over that thing. But then you multiply by the derivative of the inside using chain rule. You could do a u substitution. U equals cosine x. Derivative of cosine is negative sine. So the derivative of log of cosine is 1 over cosine times negative sine. So I'm going to throw that negative out here. And then we get, what, 1 over cosine times just regular sine. So I replace that positive with a negative. So I didn't have to write a negative over there. Some of you might have noticed that this simplifies nicely over here, but we'll get there. So now all we have to do is solve for dy dx. So I guess I'll write that over here. So dy dx equals, multiply by y times what? 2x log cosine x minus x squared sine divided by cosine. Sine divided by cosine is tangent. So dy dx is y times 2x log cosine x minus x squared tangent x. But then y equals cosine x to the x squared. So we'll just resubstitute that in for y. So cosine of x to the x squared times 2x log cosine x minus x squared tangent x. And yes, you do have to resubstitute for y. You do have to, if you can. In the implicit differentiation examples we did, well, all three of them actually, y was not solved in terms of x. But here, and in the last two examples, y was solved in terms of x, so you do want to substitute back in for that. So all of these, derivatives of inverse, implicit differentiation, and logarithmic differentiation, all of these are results of chain rule, because a dy dx just pops up from the chain rule. Now, well, for these last couple with logarithms, we introduced a natural logarithm. You could, I would recommend against it, you could use a logarithm with a different base. If you did that, you'd have a bunch of other constants showing up, because instead of, 1 over y, you'd get 1 over y log of the base. So using base e is convenient because log of e is just 1. So I would say stick with base e.